Securing the Bitcoin network requires a massive physical footprint. Facilities packed with mining hardware chew through gigawatts of power to maintain a single ledger. This defense relies on elliptic curve cryptography, or ECC. It is the specific algorithmic standard that secures most of the modern internet. Classical computers face a strict limitation against ECC because they process data linearly. To guess a private key, a supercomputer must check combinations one by one, a process that would take a standard machine billions of years. This linear bottleneck is why the math holds, keeping digital wealth secure within the vault. That security model relies entirely on the laws of classical physics. Quantum processors operate on a completely different set of physical rules. Instead of standard bits, quantum computers use qubits. Through a property called superposition, these qubits exist in multiple states at the exact same time. In 1994, mathematician Peter Shor created an algorithm designed for this architecture. Shor's algorithm uses superposition to evaluate vast numbers of cryptographic keys simultaneously, skipping the sequential guessing process entirely. By bypassing the linear maze, a powerful enough quantum computer gives the unbreakable vault of modern money a strict expiration date. This timeline maps the collision course. We are in the NISQ era. Current machines remain prone to errors. To break encryption, engineers must reach fault-tolerant quantum computing. When hardware surpasses encryption standards, we hit Q-day, when traditional defenses fail. While physicists debate the exact timing of this intersection, the event itself is a mathematical certainty. It represents a ticking clock for every secure network on Earth. For Bitcoin, the vulnerability opens the moment a user broadcasts a transaction. During this brief processing window, their public key is exposed to the ledger. A quantum actor could intercept that broadcast, use Shor's algorithm to calculate the matching private key, and forge a digital signature to redirect those funds before the original block confirms. Forging even a handful of transactions would instantly drain the core trust required to keep a decentralized currency afloat, causing the network's value to collapse. Preventing that collapse requires building a multi-dimensional defense known as post-quantum cryptography, or PQC. Lattice-based PQC restructures math from a two-dimensional curve into a dense three-dimensional grid. To crack it, computers must find the shortest intersecting vector. As dimensions are added, dead ends and looping paths become so complex that quantum algorithms get lost. With the mathematical blueprint for this shield already complete, cryptographers have developed a defense that quantum machines cannot pierce. Bitcoin functions as updatable open-source software, allowing the network to rewrite its own defensive protocols. This transition is executed through a hard fork. The network reaches an agreement to move all activity onto a new chain, armored by PQC stand-ins. Achieving this upgrade requires global consensus, a massive human coordination challenge involving thousands of independent miners and node operators. This human consensus serves as the ultimate security layer. The network survives because its decentralized community can recognize a threat and coordinate the necessary adaptation. Quantum computers will not kill Bitcoin. The impending arrival of fault-tolerant machines acts as a catalyst, forcing decentralized money to shed its aging cryptography and undergo a vital evolutionary leap. Digital money relies on continuous adaptation. To remain secure, the vault must always evolve to outpace the next apex predator trying to break in.